Hello and welcome to this video on what is multi-level analysis. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis, structural equation modeling, multi-level analysis and latent class modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources including courses that I offer through QuantFish. In this video, I want to address the question of what is multi-level analysis. And so this is a video for beginners, so to say, for those of you who have had experience with linear regression analysis, maybe logistic regression analysis, but who have never dealt with multi-level regression analysis. And so I want to clarify how multi-level regression analysis relates to conventional regression analysis and why and when we need multi-level analysis. For that purpose, it is useful to start with a brief review of conventional regression analysis, which is also known as ordinary least squares regression or linear regression. And so then we will see very easily how multi-level regression analysis is a generalization of ordinary least squares conventional linear regression. In ordinary least squares regression, we have in the simplest possible scenario a single independent variable or predictor x that is used to predict a criterion or dependent variable y, and there's also an error term that is sometimes referred to as a residual of the regression, e. And so in this model, we are predicting, for example, job satisfaction from salary. So we could assume that there's probably a correlation that is positive between salary and job satisfaction. Better paid jobs lead to higher job satisfaction. The question is, to which extent does the salary determine or predict job satisfaction? We can estimate that with a regression model, here assuming a linear relationship between salary and job satisfaction, meaning as salary goes up, we expect that job satisfaction also would increase. And you can see in this path diagram here, there's a coefficient beta 1, so a regression slope coefficient that is used to quantify the relationship between x and y. We can also express this ordinary least squares regression in terms of an equation. So this is a linear regression equation. Y is equal to beta 0 plus beta 1 times x plus e. You can see there's an index or subscript I here for the person. So this is formulated for persons in the same way as we will see later. Multi-level regression analysis is typically formulated. So I here stands for a specific individual. And then beta 0 is the intercept, which is a constant or additive constant. And beta 1 is the slope coefficient, the multiplicative constant that quantifies the linear association between x and y. And there's an error term ei that characterizes all influences on y that are not determined by a linear regression on x. That could be, for example, non-linear relationships, interaction effects, other variable effects, and also random measurement error, or non-linear effects. So all kinds of effects that are not captured by a linear regression on x alone. Now, typically we consider more than one predictor in a linear regression and they can be correlated. However, here in this case, I'm just going to focus only on this very simple example to keep matters simple. So ordinary least squares regression looks like this. Now, why do we also need to learn about multi-level regression analysis? The reason is that ordinary least squares regression comes with an independence assumption. Now, this independence assumption obviously does not concern the variables, so x and y are definitely not considered to be independent. salary is supposed to be correlated with job satisfaction, so there would be non-independence, the variables would be related, but the independence assumptions concerns the observations or persons. So the people in our underlying population and or in the sample are assumed to be independent, or in other words, there's supposed to be a simple random sample from the population where there are no dependencies among the observations. For example, the sampling shouldn't include couples, husbands and wives, or employees from the same company, so say beyond random selection where that could happen, but we don't want to have observations that are clustered in some way in higher level units or organizations. So there shouldn't be a correlation between observations. Also, that would preclude repeated observations of the same people. So say on X, so multiple times the same people would provide X scores, and multiple times the same people would provide Y scores, then we can't mingle them together in this simple regression model. And so often this assumption is violated when you have cluster data. It shouldn't be violated when you collect a simple random sample from the population where you just simply randomly draw employees from the sample that are not nested within companies or something like that. You just simply randomly select employees and then you record their salary and their job satisfaction scores, and then it shouldn't be an issue. But if you sample employees from companies, so if you sample at the company level and then the individuals who are in the same company, they are likely to be more similar to one another, which means their scores are likely correlated, and that can lead to a problem with OLS regression analysis. So when you have employees nested within companies, or when you have husbands and wives that are nested in the same family, or you have students that are nested within school classes, then you have cluster data or hierarchical data, as we say, multi-level data, nested data. So those are all terms for the same thing, which means those are this is a complex sampling mechanism that very likely leads to correlated non-independent observations. So in our example, we would have at level 1 employees and at level 2 companies. So we have a hierarchical structure then with employees that are nested within companies, and that's where you can see where the multi-level analysis comes into play, because now we're dealing with a multi-level sampling design where we sample companies, and then within these companies we have employees, so we have different levels of observations. And of course there could be more than 2 levels. The companies could be nested within states or within countries, for example, then you would have a 3 or a 4 level data structure that would be even more complex. Now, why does this pose a problem when you have nested observations like that with a multi-level sampling design? The problem is that due to the non-independence of the observations, due to the correlatedness of the data points, you would overestimate the effective sample size. And that's pretty easy to understand intuitively, because if observations are more similar than they would be if they had been randomly sampled from the population, then obviously those nested observations contain less unique information because they overlap. They're correlated, so husbands and wives in part, for example, provide the same information. Employees from the same company provide the same information in part because they are in the same structure, and therefore you have less unique information, a smaller effective sample size when you have nested observations that are correlated. Now, of importance, that need not be the case. So you could have nested observations and perhaps there isn't any correlation between those observations. However, you should check that, and I will show you shortly how you can actually measure that, how you can quantify the degree of dependence of the observations when you have a multi-level data structure. Now, as a consequence of overestimating the effective sample size, the standard errors of your parameter estimates, for example, the standard errors of regression, slope coefficients in OLS regression, would be underestimated. So this means when you have correlated observations, non-independent observations, then your standard errors will tend to be too small. And that has consequences, first of all, for tests of significance. So when you, for example, want to test your beta 1 estimate, the estimate of the regression slope coefficient for statistical significance. So if you're testing the null hypothesis that beta 1 is 0 in the population, then you estimate a standard error from your sample data, and that standard error with nested data will tend to be too small. And as a result, your test of significance, your t-test for that regression coefficient, will tend to lead to a p-value that is too small, meaning to a too optimistic result regarding statistical significance. So you will reject the null hypothesis more frequently than you should. And we call that type 1 error inflation or alpha error inflation, meaning you would incorrectly reject the null hypothesis in too many cases. You would incorrectly claim statistical significance more often than you should. So that's one problem. And another problem with standard errors that are too small, that is related to that issue of type 1 error inflation, is that confidence intervals around your, for example, beta 1 coefficient for the OLS regression will tend to be too narrow, which means they would be too optimistic about the precision of the estimation of your regression coefficient. And they would tell you again, perhaps that the regression coefficient, that the confidence interval does not include 0, meaning the regression coefficient is statistically significant at the chosen alpha level, and that may not be true. So again, this could lead to incorrect rejection of the null hypothesis when you have correlated observations. Also, in certain cases, a clustered data structure can also lead to parameter bias. So not only then would your statistical inference be compromised, meaning your tests of significance and confidence intervals, but also the parameter estimates as such. So the point estimate, for example, of the beta 1 coefficient may be biased due to between cluster mean differences. So if the clusters, the companies, for example, differ greatly in terms of their job satisfaction, for example, or their average job satisfaction and or the average salary, then those differences may lead to a covariance structure that could lead to bias in the estimation of beta 1 itself. So then not only your standard errors would be biased and your tests of significance, but also the beta coefficient as such. And that would be bad. So you can see there's some bad consequences when you apply OLS, conventional regression, to multi-level structured data, and that also applies to other statistical methods, such as, for example, analysis of variance, a t-test for mean differences, and other procedures that also would suffer from these consequences potentially when applied to nested or clustered data. Now, this is not the only reason why we need multi-level analysis, though. Another reason is that when we have variables at those different levels that are of interest, then we cannot easily or correctly analyze them with OLS regression. So let's say, for example, if we did not only have salary as a predictor of job satisfaction, but also the organizational climate, let's say. So the average or mean rated company climate by employees, then that would be a level 2 variable. So it would be a variable at the company level, or the size of the company. So maybe that also has an influence on job satisfaction, how big the company is. And so that would be a variable that would be a level 2 variable at the company level. And so in order to consider level 2 variables and or level 3, level 4 variables and so on, we have to use multi-level analysis. And so in that way, then we can take into account predictor variables at different levels and also interactions between different levels. So-called cross-level interactions can then be studied as well. So multi-level analysis is not only to prevent the bad consequences of applying single-level analysis to nested data, but it also is important in order to study variables at multiple levels. Now, how can you determine whether your observations are correlated due to nesting. Because as I said earlier, this need not be the case. Sometimes we have nested data, but there are no dependencies for the variables of interest. And in that case, then it doesn't matter. But typically it does matter. So typically we have dependencies that impact our variables, and we can measure that and quantify that with the so-called intra-class correlation coefficient. The intra-class correlation coefficient, here abbreviated as rho, the Greek letter rho IC, is given as the variance between clusters, so that's the sigma squared b in the numerator of this formula, divided by the sum of between cluster variance plus within cluster variance. So in the numerator you have the level 2 variance, and in the denominator you have the total variance component. And so that can be estimated from the data based on a model that's called an empty model or intercept-only model, which is a special type of multi-level model that estimates these variance components. And programs for multi-level analysis, such as Mplus, for example, will readily give you that intra-class correlation coefficient when you ask for it using, for example, a 2-level basic analysis in Mplus. And you can find videos on how to do multi-level analysis in Mplus on this channel here. There's a whole playlist on that you can find here. So this is a way to quantify this. And so the intra-class correlation coefficient, when it's 0, would indicate that there are no dependencies. There's no between level variance. And then that would be fine. So if you found that the intra-class correlation is exactly 0, then it means there are no dependencies. You don't have to worry about the nested data structure. However, whenever the intra-class correlation is greater than 0, that means there are dependencies in the data that need to be addressed, even if your intra-class correlation coefficient is small or seemingly small. So even if it's just like 0.1 or something like that, and you think, oh, that seems small. No, it still can have an impact on your standard errors and on your type 1 error inflation. So you want to take that into account. And so to take that into account, one way is to use robust standard error. So for example, in Mplus, you can run a conventional regression analysis, but request robust standard errors that are robust to clustering and nested data structures. That would be one way to address this. However, that would not address the potential bias in your parameter estimates, and it also would not address level 2 variables. So if you had predictor variables at multiple levels, then you couldn't easily handle them in this way. So the other way to handle correlated observations is by means of multi-level analysis. And so that is what I will show you shortly. Before I do this, I want to show you real quick how the overestimation of the affected sample size is related to the intra-class correlation coefficient. And so in this formula, you can see that the effective sample size on the left-hand side of the equation is a function of the actual sample size n. So that's in the numerator here. So this would be the sample size if you ignored clustering. And then in the denominator, you have the intra-class correlation, rho IC, and you have S, which is the mean cluster size, so the mean size of your organizations. And so you can see that the effective sample size that would take into account clustering will only equal the actual sample size n when the intra-class correlation coefficient is 0, because in that case the denominator becomes 1, and so then you divide n by 1, and so you have n effective equal to n whenever rho IC is 0. In all other cases, so whenever rho IC is positive, your effective sample size will be smaller than your actual sample size, and that has to be taken into account. So with this formula, so say the effective sample size can be estimated based on the intra-class correlation coefficient. Now let's talk about what multi-level regression analysis is. And so the first step, so say to get from OLS regression to a multi-level regression analysis, is a so-called random coefficient regression model. In a random coefficient regression model, which is a type of multi-level regression model, we have at level 1 an equation that looks very similar to our standard OLS non-multi-level regression analysis that I showed you earlier. And so at level 1, we have yij equals beta 0j plus beta 1j times xij plus rij. So again, we have an intercept beta 0, we have a slope coefficient beta 1, we have an error or residual term rij, so it's very similar. However, notice that now we have two indices here. We have an index I for the person again, and now we also have an index j for the cluster, so for the organization, which means these regression equations are cluster specific. Each cluster can have its own intercept beta 0j and its own slope coefficient beta 1j, and that's different from the OLS regression that is at a single level and does not take into account clustering. So that's the first difference. And so now, why is this called a random coefficient regression? It's called a random coefficient regression because at level 2 we're allowing these beta 0 and beta 1 regression coefficients to have a mean and a deviation from the mean, a cluster-specific deviation. So you can see that at level 2, beta 0j, the intercept from level 1, is broken down into a mean intercept gamma 0 plus a cluster-specific deviation from that overall mean intercept, and that's u0j. So that's in cluster j the deviation of the cluster specific intercept from the mean intercept. And the same is done for the slope coefficient beta 1j, which is also broken down into a mean regression coefficient gamma 10 plus u1j. And so you can see here that now we have a fixed effect gamma, so the gammas are fixed effects, those are constants, but the u terms are random effects. So there's a variance component that is estimated for beta 0j, the variance of u0j, and also a variance component for beta 1j, which is the variance of u1j. And so this is why it's called a random coefficient regression, because these beta 0j and beta 1j coefficient at level 1 are not fixed effects. They are random effects with a variance component and a mean. And so therefore this is different from an OLS regression where beta 0 and beta 1 are constants that do not vary across clusters. And so now, since we allow for between cluster variation in the intercept and slope of the level 1 regression, we're taking into account the cluster specific structure or the nested structure of the data, meaning the non-independence that arises from that. And so in that way you can take into account that non-independence by using a random coefficient regression where you have those intercept and slope coefficients vary across clusters. Now, you can extend this random coefficient regression analysis, and then that's called a multi-level regression analysis, by having predictor variables not only at level 1, like we previously saw, so the level 1 equation here is the same as on the previous slide, but now at level 2 we also have a predictor wj, and so we can have a predictor for both the intercept and the slope with its own fixed regression coefficient gamma 01 and gamma 11 in the level 2 equation. So we can predict differences in the intercepts between clusters by a level 2 predictor and differences in the slopes with a level 2 predictor. So for example, the company size could be a level 2 predictor wj, and then maybe the size of the company explains differences in the intercept and or differences in the slope of the level 1 regression. And of course you can further extend this analysis by having more level 1 predictors, by having more level 2 predictors, by having interaction effects, by having quadratic effects in there, or you could have another level potentially with more equations at level 3, maybe the state level or the country level. And so this is, so to say, very flexible in terms of how it can be extended. I hope you found this video useful to learn more about multi-level regression analysis and how it relates to standard OLS regression. If you did, please consider subscribing to this channel, and also don't forget to check out the description for additional resources, including courses that I teach on multi-level analysis for QuantFish, and I'll see you next time.